Hi everyone, this is my lab 4 for Physics 1 at Georgia Tech. So basically, the purpose of this lab is going to be examine the motion of a spring mass system, which the mass is going to swing in an arc while oscillating on the spring. And we're going to be using Tracker to analyze that, and then create a model of this movement using VPython to simulate the mass and the spring system, and examine the energy associated with that model. So we're going to take a look at the video really quickly. Alright, so you can see from the video that we're going to start from the moment Dr. Greco actually releases the mass on the spring. So it moves in this nice little circular fashion, and it moves both in the x and y direction, as you can see from the graphs. Now, one thing we're going to get from the graphs here is the period using the y coordinates, and I'll explain why that's important later. So we're going to look at a few constants that we also need to know. Alright, so using the video, I was able to find that the period is going to be 1.52 seconds. And then using this nifty formula right here, we're going to be able to find the spring constant, which I found to be 6.87 newtons per meters. And then we found using Hooke's law, which is the generic k times length relaxed and length minus the length stretch is going to be 0.126 meters. And then we have g, which is always 9.8 meters per second squared, and the mass of the mass is 0.402 kilograms. Alright, so it's important to know that there's two forces acting on the mass in this system. There's the spring force, which is just the force of the spring, which is going to act in both the x and y direction, and the weight force, which is just going to act in the y direction, and it's just going to be the ball times the mass of the mass times g. But there's going to be three different types of energy, which is going to be kinetic energy, gravitational potential energy, and spring potential energy. Alright, so now we can actually take a look at the Python code. Alright, so seeing as you're viewing this video, you're probably also in physics right now, in this specific physics, and actually had to code this yourself. So I'm not going to explain this in much detail. Here's where we put in the information, right here, where we put the information that we found. And then here's where we calculated the initial energies. We know that the kinetic energy is initially 0 because it's not moving. We know that gravitational is just going to be what I also showed in those slides. And the spring is also going to be about the same. So in this loop, we're actually calculating the change, or not the change, but the change in the spring's position. So we know that the gravitational force only acts in the y direction. So instead of putting this times L hat, which is the unit vector, which we're going to multiply by the spring energy, by the spring force, we're only going to put the weight force in the y direction. So when we calculate F net, the weight force is only affecting the y direction. And then we calculate the change of position. And here we're going to calculate the energies and the new energies and the changes in energies. And here's where we're going to graph the changes. So now let's run this really quickly. It should also run what the data that we got from the model. So let's see how that goes. All right, so here's the graph of the energies, and you can see that that when you add all the energies up, they end up equaling 0. And for some reason, Python likes to completely close on me. But it's going to look like that. Now, the model actually follows fairly closely with the actual data. It's a little bit off. That's partially due to error by me. If you actually look closer at the tracker graphs. Alright, so it cut off randomly, so we're going to keep recording from here. The energies end up equaling 0 when you add them all together. And the model actually follows very well with the actual data, as you can see from here. It's a little bit off, which is partially due to my own error, but it's also because of the period was not entirely accurate due to that, so the spring constant may not be absolutely perfect, and the relaxed length may not actually be true. Another thing we probably could have done was actually compared it to a plot of the x and y positions, which may have shown where it was accurate. Now, important things to remember is that there's no work done on the system, so the overall work is 0. This means that it actually does satisfy the work energy principle because no energy is lost in this exchange because no energy is actually put in. So you can look at the graph and you see that the total change in energy is equal to 0 because the work should be equal to 0. Now, if you remember, I said we use the y position in order to calculate the period. Well, that's because they give us, when you use the x and the y data, it gives you two different periods. When I used X, I got about 1.61 seconds, which is actually the period for a pendulum, not for the spring. Since we wanted to calculate the spring constant, we wanted to use the Y because the spring normally goes in the up and down direction, which is why you want to use the Y data in this situation. All right, so that's it, and have a nice day, everyone.